Thanks very much, Michelle. Thanks for coming today, and I hope that I can give you a flavour for one aspect or certain aspects of work we've been engaged in over the last couple of years around, I guess, water resource assessment for outback South Australia. My talk today is really about one element of the work we've been engaged in, focusing in the northwest corner of the state in the APY lands in the Musgrave province. And what I'll do is talk to, I guess, the development of a technique or an approach that we take with the use of mining company data to help set up a framework for exploring for water resources. So where do you look, particularly if you're going to develop a mine or something of that nature where you really do need to potentially get a lot of water to help develop a resource such as that. Where do you go? Where might you look? And that's really what this research has been about over the last couple of years. Now, there are a whole load of people on that slide that I have to acknowledge as contributing to this work. And, yes, I'd also like to acknowledge many more, in fact, who've contributed in one way, shape or form to the conduct of the research, the traditional owners of the APY lands, but others, some of who are in the audience, Gary, for example. We valued your contribution and help in actually conducting the work we did over the last year and a bit. Others here in the institutions, state authorities, or whatever you'd like to describe them as, DUNA and DMITA, and of course the Goyder Institute as well, and those in CSIRO. So I acknowledge them in advance. I guess the driver for the research and the work that we undertook was, were there any ways or how could we use data that is collected routinely by the mining sector in exploring for water? So quite often a mining company will explore in an area that's relatively remote. They'll be targeting regions in their tenements, and those their targets, if you like, are very much focused on where do I put a drill hole to see if I can find minerals. It's as simple as that. And they use geophysics as a technique, and there are a range of techniques in the geophysical toolbox, if you like, that they can employ. And we were interested in knowing whether we could use that toolbox, that same toolbox and the data they collect on a routine basis, to actually look at the water issue and the water resource issue. So a sort of complementary or conjunctive use of geophysics, as we like to think about it. So what we set out to do was basically to say, well, can we use this geophysical data that you collect to target where you might drill to tell us something about where you might look for water as well? So that was the sort of philosophy and a driving philosophy. As I mentioned, they're drilling or they're working in remote areas. In those remote areas, quite often we have a paucity of information about water, the water resource, the groundwater present, how quickly it's recharged, all of those sorts of things. So we have to try and get an understanding of some of that. And so part of the work we did was to get a handle on how quickly some of that water might actually, or how old was it, how quickly might it recharge if you were to extract it. So if you were going to develop a mine in a remote area, are you actually, and then you were going to exploit the groundwater resource in a local area to support the mining development, are you actually mining the water as well? In other words, taking it out of the system and for it never to be replenished, or to be replenished over tens of thousands of years, something like that. So we had to try and understand that as part of the framework of water resource assessment. And that's ongoing within the departments here as well. Just step back a moment. Water, it's a key part of any sustainable minerals industry. I think most of us might accept that. But if you actually look at some of the figures that are floating around in the mining sector in South Australia, there's this huge resource demand, almost threefold increase anticipated between now and 2019 in terms of, and that's water that would be required to support the development of mines and their ongoing sustainability, if you like. In Western Australia, it's a different order of magnitude again, very, very significant. So this is an issue that is right across the country, if you like, in driving a sustainable minerals industry. We need this knowledge and this background and this context. One of the interesting things when we started with this project was a very receptive mining sector. Companies who said, yes, we understand the importance of water in our industry. We understand the importance of understanding where it is, how much there is, where it might not be, or what quality it might be. Because if we ever found something and we wanted to exploit it, we will indeed want to go and find water to help develop that particular mine or whatever. So they were very receptive to the idea of embracing the project and embracing the idea of using their geophysical data, their company data, in a way that might be useful to them in the longer term. So some of those data sets we worked with look something like this, things like, you can see it better up here, but things like this, which is what we term an airborne EM or electromagnetic data set, tells us about the conductivity of the ground. This image over here is about the gravity of the ground in the subsurface. It tells us about the density of rocks and their variation. And these are the same areas, but you can see here what we term a paleo valley. In here, it's picking up the same thing, but in a different way. It's telling us something about the water contained in that paleo valley. So you've got complementary sets of information contained in these geophysical data. The key thing about geophysics is it tells you what's happening in the subsurface, so we're getting a three-dimensional picture about what's going on, and that's the key thing about these data sets and their value. What we were also concerned with is trying to be able to say, well, if we know what's going on over here, for example, and we have data over here, can we make a prediction about what's happening over here where we have no data? So are we able to come up with a technique or an approach that allows us to extrapolate from the known to the unknown? And part of that, or part of the driver in the research, was to say, well, how do we treat data that allows us to extend our understanding of areas from small patches of information to areas where we have no data at all? In a geophysical sense, we find that data is acquired by a whole range of geophysical systems that all give us slightly different bits of information, and we have to convert that to something that's common and is extrapolatable easily. So we go from things that these are sections through the earth, shown here in the lower two sections here, that tell us about the three-dimensional conductivity structure of the ground. But we can transform that, and this is what we chose to do, where we chose to create a map of the ground conductivity, pick up places where we would anticipate there to be the presence of paleo valley sediments or something like that, in other words, aquifers, and be able to then say, well, our knowledge of the information contained in these sorts of data tell us something about the quality of the water contained, the geometry of those aquifers, and from that information we can say, okay, well, if we went over here where there's a similar pattern and we see the same things, we can make an inference about the properties of the aquifers present in these other areas. So that was some of the driving elements of what we were doing. I think it's accepted that in many parts of South Australia, particularly in the non-prescribed well areas, so that's up in the north, up through here, but similarly up around this northern part of South Australia, the knowledge of groundwater resource and its availability and the quality of it is quite scant, if you like, in a general sense. We just don't have enough information about the water and what it looks like and what the aquifers look like. Sorry. So the Flows project, just to quickly move on, had a set of three priorities. First of all, in remote areas, could we identify the geometry and characteristics of aquifers and the water they contained and get some feel for their potential capacity? That's where we used the geophysics. We also tried to then tie that in with some on-ground investigation with particular bores, where we looked at trying to understand the age of the groundwater and the rate at which that groundwater was replenished over time. Then we did some other desktop studies relating to groundwater-dependent ecosystems and cultural assets and the like, all quite important. These were the two primary areas we chose in the first part of Flows, up in the northern Musgrave region, or the APY lands, particularly up there. Another part of our study involved the Frome embayment. The Musgrave block, or the Musgrave province, is very prospective for the minerals industry, and so it has significant potential to identify mineral resources that could be exploited. But in that region, there is a lot of information about water, but it varies. Most of the information exists on the northern part of the ranges and over here. Not a lot down in these regions through here, which are all prospective from an exploration perspective. I'll keep ticking along. So the Musgrave Province has a complex geology. I won't spend too much time describing this, but it's very prospective for nickel, copper, gold, a whole load of minerals, uranium, and the like. So very prospective terrain. Exploration is still underway in many respects. It's in its infancy through that region, so it's got a considerable potential for there is considerable potential for identifying resource there, mineral resources, and therefore a potential demand for water resource to support that industry as well. It's generally known through people in the audience that a lot of the groundwater is contained in weathered and fractured rock parts of the higher ground, but also the presence of paleovalleys is also known, and they contain and are known to contain water of varying quality. As you go further south in the APY lands, you get onlapping basin sediments in the Officer Basin, and they too also contain water. So we undertook a review of what existed. Some of these bores have been drilled by or worked on by some of our audience members. Quite considerable. When you look at this, and all the dots are bore locations, there may not be every single one there, and in this particular case it indicates the quality of the groundwater right through the APY lands. And on top of that, there are a series of paleovalleys mapped in this beige colour through here. So you can see the quality of groundwater is quite variable. The blues relatively good quality, the reds and oranges less good quality water. One of the general trends you observe, and we'll come back to that in a minute, is that up on the ranges in the northern part of the APY lands, things are relatively fresh. As you come away from the ranges further to the south, or down here, for example, then the quality tapers off, if you like. The quality of the water tapers off. What we did in the first instance was go to the mining companies and say, give us your geophysical data, because we'll work with it and convert it to a form that allows us to identify these conductive zones that might relate to paleovalleys particularly. So we ended up with essentially a series of postage stamps, and you get these postage stamps, which might be, oops, sorry, ooh, that was a bit too hasty. Sorry, you get these postage stamps, small areas that they fly with their geophysical instrumentation, and they look for mineral targets to drill. So single targets, they'll look and they'll drill them. But the information contained in these spatial data, these geophysical data, tell us something about the subsurface. And you can see these dendritic patterns within this up through here, for example. And these are patterns that relate to the subsurface drainage, an old drainage system that once crossed right through this landscape. And that's what we're picking up in these data sets. But it's a fragmented coverage, if you like. So we're seeing a fragmented coverage of these paleo drainage systems that extend right through this area, through these, if you like, windows into the subsurface, which is what we're picking up here. Our philosophy was to work with those data sets. These are just sections from different systems, and that's what we had. If you go back to that previous, each of these data sets is acquired by different sensor systems, so we have to treat them in a certain way such that the information content from one area can be compared with another area and then extended more readily. We can then translate some of that information into things like the thickness of the cover, And so that's what this image tells us about. It tells us about how thick the unconsolidated materials or the weathered materials are in the land surface sitting on solid bedrock. And so this is a map here of the thickness of regolith going from about, it's hard to work out from this angle, but greater than 75 to 80 meters from zero. So in these parts of the landscape, we've got much thicker sedimentary sequences than we do where it's yellowy yellow patches like this. Okay, so what you pick out quite clearly is a very complex drainage or paleo-drainage system. And when you look at it in 3D or in a perspective view like this, and you look at the current topography, which is what I've got up here, we've got a very flat landscape in the current environment, but in the subsurface, a very complex drainage system. This is the paleo topography. So if you like, this was the topography tens of millions of years ago. This is how the landscape eroded, and it then filled in slowly. And it filled in with these sediments, and the valleys filled. And those sediments that now infill these valleys are the current aquifer systems that cross this whole landscape. One of the interesting things we also noted with this interpretation is how the subsurface patterns of drainage are very strongly controlled by the geology. So you see these lineations or linear features. So you can see that this feature through here, which is the one that I've pointed out, is very linear, and the reason it's linear, and that's this feature here, the reason it's linear is it's following a fault system. And you can see that in another geophysical data set. You see these long linear features running through this landscape. These are faults and structures and boundaries between different lithologies. So right through this region, you've got these deep-seated faults, and the original drainage, when it developed through this landscape, etched out along these old fault systems, these ancient fault systems, along boundaries between different lithologies, and then subsequently they got filled in by sediment coming in and washing off the high ranges and filling them in essentially and creating these aquifers. With these geophysical data sets, we were able to then say, well, okay, what we do understand about this landscape is that we've got structurally controlled paleo-valley systems that we can infer might be present, for example, down here or up through here or down through here maybe, where we don't have this information from these airborne EM data sets. So we're able to use the geophysical data in a complementary way to actually pinpoint where you might go if you were to try and explore for water or these thicker aquifer sequences where the water might be contained. So in a simple schematic sense, conceptually, and this is where we were trying to go, in a pre-Pliocene landscape, in the west and central Musgraves, you might have had a landscape that looked like this, eroding out. It then filled in, so that's the contemporary landscape. And these are the current aquifers. They may be valley fills, sands and gravels, or silts and clays, or even calcrete systems. And then that got covered with a sand sequence as well. And then on top of that, you now get contemporary alluvial, colluvial movement of materials off the ranges as well. So we've gone from that in the pre-Pliocene to the contemporary system, but these essentially are our aquifer systems where most of the groundwater would be contained and where you would target water resource if you were developing a mine in this landscape. We then just chose to extend that out right across the Musgrave province to make sure that we were on the right track in saying, yep, we could use the geophysical data to tell us something about what's going on in this particular case up in the northwest, but did it hold together for these areas over here, for example, and further to the east. And we were able to then check that against things like available drilling, where you could actually look at the aquifer systems and say, yes, we get a handle on what's going on based on looking at these different data sets. The other thing that we did do is look at it in relation to the contemporary topography. So this is a map, or an image, if you like, of the flatness of the landscape. Okay, so where the pale colours are, the landscape is relatively flat. Where it's dark, the landscape is steep and you're in the ranges. Okay, and you see, if you look at a map like this, it says the contemporary topography has these large, wide paleo-drainage systems, large, wide contemporary valley systems, or areas where the landscape is extremely flat. Then it has these subcropping, outcropping areas where you've got fractured rock systems and localized aquifers as well present. So we used this, and we used it in a certain way with the geophysical data set we had. So this is now the airborne electromagnetics, so the geophysical data sitting on top of that topographic index. What we wanted to do is to see whether there was any association. Is there an association with the paleotopography or the paleo drainage patterns and the contemporary topography? Because if there is, could we use one to extend our understanding and develop a framework right across the region? And then could we think about the same approach elsewhere in the APY lands, right down even to the coast or in the Northern Eyre Peninsula or whatever? So what you see in through here is in these low flat areas, and that's up through here as well, or in there for that matter, you see these complex paleo drainage patterns. Let's zoom in on one of those. So in the low flat area, so that's this area here, and it's bounded in there, you get these paleo valley systems or paleo drainage systems. And then on the margins, and sometimes they actually cross-cut some of the higher, less flat areas in the contemporary topography. So that's saying even in those less flat areas, we've got valley fill that is a potential area for some water to be present in this valley fill sediment. We followed that up with other data sets and looked at it in relation to existing borehole data where present. And one of the great things is we can look at things in a spatial sense, in a map form sense, but we can then relate that map form to a three-dimensional view of things or a section form. So we take that line of data there through that image, project it, now a map of conductivity with depth down here. So this is about 200 meters depth. You can see these fill sediments, which are these conductors here and here. And then there's a range there, and a little hill there. But essentially now we're getting to geometry of the aquifer systems as well from this data. That's how we worked with it. So we looked at the contemporary landscape. We compared it to the paleo landscape and the paleo landscape drainage that was being identified in the geophysical data and said, are we seeing a relationship? Is there a relationship? And the answer in simple terms was yes, there's a relationship between the paleo drainage and the contemporary landscape. So where you get paleo drainage, it's usually present in the low flat areas of the contemporary landscape. Right? So in other words, the contemporary landscape in some way mirrors that paleo landscape, or where you'd have where you did have preferential drainage development back in the pre-Pliocene. Well, that's good, because what that allows us to do then is to say, okay, we can take that understanding, and I'll just flick through here, we can take that understanding and then build a framework that's extendable right across the Musgraves. So a hydrogeological framework from this localized study, but we can extend it out, and the relationships we've established. So what we did was to say, okay, the low flat areas are areas where we are likely to have alluvial, colluvial, but paleo valley sediments present. We know that from the geophysics up through here or down here. So these areas, which are the low flat areas in our contemporary landscape, are likely to have present in those areas deeper sequences of paleo valley sediment, which are your targets if you wanted to look for water. So if I found a mine, for example, here in this outcropping area or subcropping area, the places I'd look for water would be here or here, where I would expect to find more water present in these paleo valley systems. So that's the framework we've got, and we then extended that out. We tested it, sorry, I should say. So these were some of the data sets. We then got another data set later on in the exercise up on the northern part of the survey area, which had indeed been drilled in one area, particularly up through here, where you see the reddy pink areas up there, and they correspond to these paleo valleys. These are paleo valleys as well. A company who got these data drilled it, established it with a thick paleo valley sequence, very high yielding sequence, good quality water. They're interested in that because they've got a mine actually on the WA side as well, not on the South Australian side. But it held together, the framework held together, and it was extended and tested with these other data sets that were present and with drilling. So as I flagged up through here, drill hole up there, that was tested by the company. The other thing that we looked at elsewhere in the Musgrave province are the use of magnetics. So if you actually look at the data sets, the regional magnetics, which I have here, and it's been processed in a way to highlight structure, you can see a change in the texture of the information contained in that magnetics image. And that texture is indicative of changes in the thickness of sediment sitting on top of that crystalline basement. So here we have a map on on this side, which is magnetics, but we see a change in texture away from this sort of very linearly, highly textured sequence to this sort of flatter, less textured sequence. And that's actually related to the Levanger graben. It's basically an area where we had a down faulting and valley fill or sedimentary fill into that landscape or that part of the landscape. So we've got a thicker sequence of sediments in those locations. So the magnetics is identifying where they are, those areas are. And we can look at that in the context of our regional framework, which we've identified, and you can see that if you looked in here, you might find very much thicker sequences of sedimentary materials, which is a thicker aquifer system. So we continued to do that, but we extended it right out across so it's an upscaling exercise, right out across the Musgrave province. Now, where would you go in that region if you were looking for reasonable quantities of water and wanted to support, say, an industry that you might be developing? And the low flat landscape, or so low flat contemporary landscape, are areas where you'd start because they are likely to have the thicker Paleovalley sequences present. So that's how we did it. And we tested that again by looking at other isolated patches of data, which all held up, where we got these data sets present, or even out here, but this is out into a basin sequence on the margins of the Musgrave province, so it's slightly different patterns you're seeing here. But within the Musgrave province, you certainly see that the framework was holding up. Where you got paleovalleys identified in the geophysical data, they were in the low flat parts of the landscape. So that gave us confidence about this framework and how it could be employed if you were looking for water. You can then look at it in the context of contemporary patterns of sedimentation and cover. So we can see that framework in the context of contemporary sand cover as well. And in some cases, that sand may indeed be an aquifer in its own right. We then also looked at it in the context of groundwater salinity, and you can see patterns. This is basically the same set of information I flagged right at the early part of the talk, so I won't labour too much. But if you look at things like groundwater chloride, and we went out and did some investigation work on a sequence of bores right across the APY lands. But what you do see quite clearly is a pattern of increased chloride content in the groundwater as you come away from the ranges, which are up here. So we're saying that in areas away, further down in the province, further to the south, basically your quality of groundwater will deteriorate in these Paleovalley systems. And that's reasonable sort of logic. It holds up. When you look at the hydraulic gradient for where we have groundwater contours right through the area, you can see that the gradient indicates groundwater flow is that way, down that way, and away that way. And these would be down these contemporary systems, contemporary valley systems. That's the flow direction of the groundwater. It's very slow. It's likely to be extremely slow, but those are the flow paths of these larger flow systems, if you like, right through the area. As I mentioned at the outset, the other thing that we did look at was issues around groundwater recharge. How quickly does the groundwater recharge? How old is it? And we can get a feel for recharge based on understanding the age of the groundwater. And we looked at several traces, particularly carbon-14, but also helium-4, which are indicative of the age of groundwater. If we test for these traces, we can get an idea of whether the groundwater is very old or not so old, depending on the particular technique employed. Those were just two that we looked at. We looked at others as well. And there's a sort of indicative trend in this particular case, the helium-4 data. Helium-4 is an interesting tracer. Its concentration in groundwater increases over time in a linear way. So the older the groundwater is, helium increases its concentration over time. So if you think of a flow path of groundwater from the hills up here, flowing down to the south through these old Paleovalley systems, you would expect to see the concentration of helium increasing as you move south. And those general patterns hold up. So the highest concentrations of helium are down in the southern part of the APY land, similarly over here. We do find the odd anomalies like that one up there, and these may be areas where you basically have just an internal drainage, confined drainage, where there's no escape of the groundwater. It just sits there. It accumulates helium over time, and that's all it does. So it accumulates that way. But the trends and the patterns certainly indicative of the flow paths, long flow paths, very slow movement of time. Of water across that. So the work that colleagues at Land and Water and indeed at Flinders did established that there were two sort of processes going on in terms of recharge. So in the north, in the Precambrian rocks and the ranges in the north, you've got both direct recharge, so water coming or falling onto the hills and basically going into fractures and recharging directly very quickly. Then another sort of what we term diffuse recharge, where it spreads out across the landscape and it slowly seeps into the subsurface. Mean residence time up near the ranges, so that's up in the northern part of the landscape, very young water. So it recharges extremely quickly. So that's indicative of direct recharge into the fractures and into alluvial systems right up against the ranges, very quickly recharged. That's the sort of, certainly the information that we got back was telling us. And that's not inconsistent with other observations made in the area as well. Where you get the rapid recharge and the direct recharge close to the ranges, the groundwater tends to be reasonably good quality, and indeed it's tapped at the moment for supporting the communities up there as well for that reason. So you get, and the recharge is primarily a consequence of episodic rainfall events, so high intensity events, direct recharge, good quality water. As you move away to the south and well into the sort of Quaternary or the Cainozoic sediments further south, we see a diffuse recharge starting to dominate as distinct from a direct recharge process. Where you get isolated granite outcrops, certainly adjacent to them, you'll have direct recharge influencing the age of the groundwater and its quality. But as you move further south and as you move away from those subcropping areas into the broad valley systems, very slow groundwater movement, the age of the water increases significantly. And you get higher concentrations of helium, and the carbon-14 and chloride also increases, i.e. the salinity of the groundwater is also increasing through evaporative concentration over time. Those are the sort of patterns. So we came up with an approach, so sort of heading to the conclusions now, where we work with geophysical data, where the industry's got it, where the mining sector's got it. We work with regional publicly available data sets like digital elevation data and the like, putting those together to come up with a framework which allows us to understand or develop a conceptual model and then develop a framework which we can extend out from local pieces of information, local areas. So it's been tested in the Musgraves. It seems to hold up quite well. The patterns and processes are all consistent, if you like, but we think it has application in other parts of the AW-NRM region and further down into the Gawler Ranges and the Northern Eyre Peninsula as well. And that's where we'll be trialling it next time around. So we've sort of come up with a workflow that you might identify and adopt if you were a hydro consultant working for a mining company. We've got the framework, we've got the physical hydrogeological framework in place. You might identify close to your area of interest these sorts of areas here, these beigey areas, pale yellow areas. You might then do some drilling to identify the nature of the aquifer and then characterize the resource over time. But that's the sort of strategy we'd adopt. You could just target transects of drills across here or just take the odd one. The thing is, with the odd drill hole, you might not actually pick up where the deepest part of the Paleo Valley sequence is, so we'd advocate maybe traverses of geophysics or something like that to identify where those are in a local sense. So we think with this conjunctive use of geophysical data sets, we've got a reasonable handle on what the conceptual conceptual hydrogeology looks like. We think that working with geophysical data in a consistent way allows us to extend information from a local area to a regional area to generate seamless maps, if you like. It was a very interesting exercise interacting with the industry. whilst they are very protective of their geophysical data in the first instance, they regard it as their IP and their investment and their knowledge. If you talk to them about water, they're very giving about letting you have it to look at it from a water perspective. Very keen to think about ideas of how we extend information and generate information when companies are targeting particular prospects. How can we do that? So one idea we've come up with, and I'll zip through to this, is so if you've got a company working here and it's flying a data set there, well, it doesn't take much to extend a line out of geophysics data out across a region where there is no information and the costs are relatively low. So this is something we're talking to Demeter with about. So if we wanted to extend a survey, it only costs you $1,000 or a few $1,000s, but it will give you a lot more information about the regional hydrogeology for a relatively low cost, a lot lower cost than flying your own geophysical survey. So capitalise on the fact that the mining companies are working in areas, just add a few bits of data on top of it from a state perspective, and you'll get more information about the resource potential. Critical, I think, in any of this sort of framework work is link it to understanding the age of the groundwater, how quickly it recharges, because that tells you whether you're dealing with stuff when you mine it and when you extract it, you're dealing with a mining the water situation rather than replenishable, regularly replenished resource. So these are issues to consider. Having said all of that, our knowledge about the Paleo Valley aquifer systems in the Musgrave is still extremely limited. We know very little about the variability of the materials, their transmissivity, the quality and local variation, and the yields of these systems. So there's still a lot of work to be done. And I think that's all I wanted to say. Thank you.